Your 64 GB machine chokes on 100 GB datasets. Polars solves this by decoupling the logical plan from physical execution. We are not loading data, we are defining a computation graph. This graph, the LazyFrame, only holds instructions. The critical difference is the scan operation. Instead of using the memory-intensive read_CSV function, you must use scan_CSV or scan_Parquet. This immediately enables the streaming architecture, preventing memory spikes by avoiding full materialization of the dataset into RAM. This approach is mandatory when the dataset size exceeds 80% of available system memory. The LazyFrame object is a directed acyclic graph representing the entire transformation pipeline. When you chain operations like filter, GroupBy, and select, Polars does not execute them. It only appends nodes to this graph. This deferred execution allows the engine to analyze the entire workflow before touching the data. This analysis phase is where Polars applies its query optimizer, rewriting the user-defined plan into an optimized physical plan. This optimization is crucial because it determines the order of operations, specifically prioritizing data reduction steps. The scan functions, such as scan_CSV, return a LazyFrame immediately without reading the file header or inferring data types. This is a zero-cost operation in terms of memory. Conversely, the read functions immediately attempt to load the entire dataset into memory, failing if the data volume is too large. For Parquet files, scan_Parquet leverages file metadata to understand column types and partitions without full ingestion. This metadata access is essential for enabling efficient predicate pushdown later in the pipeline, minimizing disk input-output operations.
The actual streaming behavior is triggered by the collect method, specifically when passing the streaming equals true flag. Without this flag, Polars attempts to optimize the plan for speed, often requiring more memory for intermediate results. With streaming enabled, Polars executes the plan in small, fixed-size chunks, typically processing 100,000 to 500,000 rows per chunk. This ensures the working set remains within the cache limits. The engine manages the intermediate results on disk or swaps them efficiently, guaranteeing that the peak memory usage is predictable and controllable, independent of the total dataset size. Predicate pushdown is the most effective optimization for streaming performance. By applying a filter early in the LazyFrame chain, for example, filter (pl.call) timestamp greater than date limit, Polars pushes this condition down to the data source scan. This means the engine reads only the necessary rows from the file system, skipping irrelevant data blocks entirely. This drastically reduces input-output operations and the volume of data entering the processing pipeline. Always define your filters immediately after the initial scan operation to maximize this efficiency gain. Projection pushdown minimizes the width of the data chunks being processed. If your source file contains 50 columns, but your analysis only requires 5, use the select method early in the LazyFrame chain. Polars pushes this column selection down to the file reader. The engine only loads the required 5 columns into memory for each chunk, ignoring the other 45 columns entirely. This significantly reduces memory footprint and processing time, especially when dealing with wide datasets. Combine projection and predicate pushdown immediately after the scan for maximum resource efficiency.
GroupBy operations are inherently memory-intensive because they require aggregating state across the entire dataset. In streaming mode, Polars handles this by using external sorting and hashing algorithms. When the intermediate hash table exceeds the configured memory limit, Polars spills the data to temporary files on disk. This ensures the operation completes without crashing the system, albeit at the cost of increased latency due to disk access. Monitor the temporary directory size during large GroupBy operations to confirm the streaming spill mechanism is active. Joining two large datasets requires careful planning. If one dataset, the right side of the join, fits comfortably in memory, load it eagerly using the standard read function. Polars can then broadcast the smaller frame efficiently. If both datasets are larger than RAM, Polars must use a streaming hash join. This involves partitioning both datasets and processing the join chunk by chunk, often requiring external sorting. For stability, ensure the join key is indexed or sorted in the source files if possible, minimizing the need for expensive in-memory sorting during the streaming process. For production stability, explicitly limit the memory Polars can consume. Use the set_available_physical_memory function to cap the memory usage. This prevents Polars from consuming all system resources during unexpected spikes, forcing it to rely on its streaming spill-to-disk mechanism sooner. Setting this limit slightly below the system's physical RAM ensures the operating system and other critical services remain responsive. This is a mandatory configuration step for any system analyst deploying streaming pipelines.
The final step involves integrating the collected result into your application. Since the output of collect is a standard data frame, you can immediately serialize it to a target system, such as a database or a new Parquet file. For continuous data ingestion, wrap the LazyFrame definition and the streaming collect call within a scheduled task or a microservice endpoint. This ensures that the entire process, from scan to output, operates within defined memory boundaries, providing a robust and scalable solution for handling data volumes that previously required distributed computing frameworks.